afternoon, everybody. My name is Mauro Ricotta. I'm from the University of Padua. The other authors are Professor Azzori and Professor Meneghetti from the University of Padua, Dr. Sanità from Electrus SPA, and our student Davide Refosco from the University of Padua. The industrial use of calcium carbonate filled polypropylene in structural application dates more 20 years, thanks to its capability to be molded in complex geometry, low manufacturing costs, and so on. And recently, cost reduction was achieved by introducing the material fraction of recycled polypropylene or using totally recycled polypropylene. However, in the technical literature, there is few data about the static strength of recycled polypropylene, and therefore the aims of this work were to analyze the static and fatigue behavior of different polypropylene compounds, and the analysis in the case of static and fatigue damage evolution of different type of polypropylene, and finally analysis of static and fatigue notch sensitivity. Three different materials were investigated. 42% calcium carbonate filled polypropylene, here named as EA209, a 42% weight calcium carbonate filled polypropylene, adding a 25% of recycled polypropylene, here named as R2025, and finally a filled calcium carbonate totally recycled polypropylene, here named as R2100. The notch sensitivity was investigated by using three different geometries: a 10 mm semicircular notch, a 2 mm radius U notch, and a 0.5 mm radius U notch. Test conditions: we have performed tensile statics test under displacement control according to international standard, fatigue test under load control and by imposing a load ratio equal to -1, that means push-pull fatigue. The test frequency was ranged between 1 and 22 Hz depending on the applied stress amplitude in order to maintain the material temperature below 30 degrees. The temperature was monitored by gluing a thermocouple at notch tip, and the damage evolution was investigated by carrying out dedicated tensile, static, and constant amplitude fatigue tests, and the damage was monitored on board by using a digital microscope. In this slide, you show a typical stress-strain course, and the main material properties, mechanical material properties, are summarized in this slide. And we can see that we have found 20% of reductions in terms of elastic modulus in the case of completely recycled polypropylene with respect to the original filled polypropylene. The same decrease in yield strength was found, 19%, in the case of fully recycled polypropylene with respect to the EA209 material. This table has summarized the specimen results obtained in the case of notch specimen, and keeping in mind that the increment of the theoretical stress concentration factor is equal to 3.6, reducing the notch radius from 0.5 mm to 10 mm, we can see that in the case of the first material, the yield strength is constant from an engineering point of view, and therefore if we define this simple ratio, the yield strength evaluated in the case of 10 mm with respect to that evaluated in the case of 0.5 mm, this ratio is practically 1. Similar results were found also in the case of 32025 material, that means having a 25% of recycled polypropylene, and we can see that the same ratio is equal to 1.1. And also in the case of totally recycled polypropylene, the ratio was equal to 1.12. Therefore, all tested materials resulted practically insensitive to notches in the case of static tests. In order to understand the damage evolution in the case of static tests, we have observed the specimen from two different points of view. Lateral view, that means we have a look inside the notch tip, and also from the front view. And we have found that the main results, the main useful results were found by observing the specimen from the lateral view. This is shown as an example. This is the completely recycled polypropylene in the case of 10 millimeters notch radius. This is the notch tip looking from the lateral view. We can see that damage evolution starts with several number of small voids. Some of them grows and join together to form a single big void. And when you can see in this slide, you can see that when the specimen is not completely broken, this big void passes completely through the width of the specimen. In fact, you can see the light that comes from the opposite side, and therefore this final mechanism is the final failure. Practically, the final is the case. The big void causes the final failure of the specimen. This type of observation were carried out for all materials here analyzed, for all the notch, and we can conclude the damage mechanism and their evolution were independent of the type of material and notch radius, and consisted in void formation and coalescence at the crack tip. We move to the fatigue results. In this slide are summarized all the fatigue data available at the moment in the case of plain material in order to analyze the influence of the fraction of recycled polypropylene. And we can see that the unrecycled polypropylene can be analyzed as a single series with the 25% polypropylene, and we have found a reference fatigue strength evaluated at 2 million cycles equal to 11.2 megapascal. Otherwise, the completely recycled polypropylene was analyzed as a single series, and the same fatigue strength, the reference fatigue strength evaluated at 2 million cycles was equal to 9.78 megapascal. That means that there is a factor, the reduction factor of fatigue strength equal to 1.15 by using totally recycled polypropylene. The influence of notches in the case of the fatigue loadings are summarized in this slide. Here, the first figure represents the fatigue results available at the moment in the case of completely unrecycled material. And here we can see that the specimen having 2 or 10 millimeters notch radius can be considered as a single series, while the 0.5 millimeters notch radius, due to the small number of data available at the moment, were not statistically analyzed. Therefore, we can see that at 2 million cycles, if we compare the fatigue strength in the case of plain and notch material, we can see that practically this material is notch insensitive, at least at high cycle fatigue life. Similar results were found also in the case of 25% recycled polypropylene. Also in this case, we have considered as a single series the notches having 2 millimeters and 10 millimeters radius, and we have found a reference fatigue strength equal to 11.3 megapascal. That means a reduction factor due to notch equal to practically to 1. That means also in this case that material is notch insensitive, while in the case of 0.5 millimeter notch radius, the reduction factor calculated with respect to the plain material was equal to 1.15. Finally, in the case of completely recycled polypropylene, we can observe that the 3 notches can be considered as a single series from a statistical point of view, And therefore we have calculated the reference fatigue strength at the evaluated 2 million cycle equal to 8 megapascal, and therefore we have calculated a reduction factor with respect to the plane material equal to 1.22. Therefore, we can conclude that in the case of completely recycled polypropylene, there is a small but not a small influence of notch. Finally, there is an example of damage evolution in the case of push-pull fatigue. Also in this case we are observed the specimen from lateral view. Therefore, here we have not more, probably the monitor is not representative of the picture, but here is a specimen. This is a specimen thickness. This is the notch tip, and the damage evolution is consisted in material whitening at the notch tip, and proceeding during the test. This is an example in the case of completely recycled material and 0.5 millimeter notch radius. In the case of high cycle fatigue, we can see that whitening is propagates completely through the thickness at about 70% of the total fatigue life. We can see the formation of elongated voids in the thickness direction, which propagate through the thickness, mainly through the thickness, and finally there is a sort of big void equal with the area length equal to the specimens of the thickness. And if you at the same, this is the same picture taken from lateral view and from the specimen surface, we can see that the specimen surface, this crack is not detectable from the specimen surface, but is, there is only a material whitening. Therefore, it's fundamental in order to understand the damage evolution to observe the damage evolution from the lateral view, because from some specimen surface we don't have the completely the idea of what happens inside the material. And this is we have performed this type of analysis for the three material here analyzed, and also for all the notches. We can conclude that in the case of fatigue, also it should be better, also in the case of fatigue loading, damage mechanism and their evolution were independent of the type of material and notch radius, and also consist in void formation and coalitions. Here, as an example, characteristic fracture surface observed for the same specimens that we had shown just 1 minute ago. We can see that the gray zone is the zone where the fatigue, the crack propagates from the notch toward the center of the specimen, and the white area is that due to static and final. Therefore, I move to the conclusion. We can conclude that concerning the static behavior, it was found that the yield stress decreases of about 20% by using fully recycled material with respect to the original compound. All tested material resulted practically insensitive to notches in static tests, and notch insensitivity exists also in the high cycle fatigue regime for complete original compound and 25% recycled polypropylene. And it was found that the static damage mechanism and evolution were independent of the type of material notch radius and consisted of void formation and coalition, and the same results, same mechanisms were observed also in the case of fatigue damage evolution. Thank you very much for your attention.